Hello everyone. This video is about the potential energy curve. If you look at the figure below, you have a ball sliding down an incline. Initially, all the energy will be gravitational potential energy, and this will represent the total mechanical energy. As the ball slides, it will lose elevation, so its height will decrease, causing the gravitational potential energy to decrease. At the same time, it's gaining velocity. So the height is decreasing and the velocity is increasing, and hence the total mechanical energy, E sub t, will be the sum of the two. When it reaches point B, its potential energy, its gravitational potential energy will be minimum, while its kinetic energy will be maximum. It will have its maximum velocity. Then it will go up, losing part of its kinetic to potential, and then back here to C, where it's gaining some kinetic, and then up to the same height, D, which is equal to A, assuming there is no friction. In that case, the total mechanical energy is constant, and the ball did not lose any mechanical energy. Its mechanical energy is conserved. We can represent this figure by a graph of energy versus position, where this graph compares the kinetic energy to the potential. You can see here the horizontal line representing the total mechanical energy of the system, which is kinetic plus potential, and it's constant. It does not change throughout the motion of the object, while the kinetic and the potential will be exchanging values. Whenever the potential energy is decreasing, the kinetic energy is increasing, keeping their sum constant. Now let's look at an example where the total mechanical energy is not constant due to friction. Here we have work done by non-conservative forces, and we know when there is work done by a non-conservative force, the final mechanical energy will be less than the initial mechanical energy, where the equation will be the initial mechanical energy minus the work done by the friction is equal to the final mechanical energy. We are given the mass of the roller coaster car, and we are given its initial height. So we have the initial potential energy, and it starts from rest, so its kinetic energy initially is 0. So this is the initial condition, and the final condition will be at height of 25 meters. So here will be the final condition. Now we are told that it will be able to travel up to the 25-meter height, meaning at the final position here, the final velocity is 0. And the same thing here, the initial velocity is 0, so the final kinetic energy is 0. The question is about the average friction, and we are given the distance here to be 400 meters, so this represents the whole path that the roller coaster car has taken. So now we'll go ahead and plug the values. The initial potential energy will be the mass of the roller coaster times the acceleration due to gravity times the height minus the work done by the friction, which is our unknown, times the distance, which is given to be 400 meters. This is the left hand side here, which is the initial mechanical energy minus the dissipating work of friction. This is equal to the final potential energy, which is 1000 kilograms times 9.8 meter per second square times the final height, which is 25 meters. So we have one equation with one unknown. So now we solve for the friction. 1000 times 9.8 times 40 meters will yield 392,000 joules minus the 400 meters times the friction. This is the left hand side. The right hand side of the equation, 1000 times 9.8 times 25 will yield 245,000 joules. Now we solve for the friction. This will give us 147,000 joules divided by 400 meters, and hence the force of friction, rounded off to 3 figures, will be around 368 newtons. In this problem, we are given the mass and we are given the velocity at the initial and final position, And the figure represents the graph of potential energy, gravitational potential energy versus position. So we are told at position x equal to 0, which is this position here, the velocity is 2.3 meters per second. While at position equal to 2 meters, we are asked to find the final velocity. Now, since this is a potential energy versus position graph, we can tell the magnitude of the potential energy at any point. So at the initial position here, the potential energy is 9.35 joules, while at the final status, the potential energy is 4.15 joules. Also, we are told that this is a conservative system, meaning the mechanical energy is conserved. So we apply the equation of the conservation of mechanical energy. The initial mechanical energy is equal to the final mechanical energy, and we plug the values. So that's the initial kinetic energy plus the initial potential energy, which is 9.35 joules. This is the left hand side of the equation. This is equal to the right hand side. I'm going to write the right hand side on the next line. So this is equal to the final kinetic energy, which is 1/2 the mass times the final velocity square, which is our unknown, plus the final potential energy, which is 4.15 joules. And now we rearrange the equation to solve for the final velocity. The initial kinetic energy will come out to be 4.232 joules, keeping all the significant figures until the end, plus 9.35 joules. This will be the left hand side. On the right hand side, we'll have 1/2 times 1.6, which is 0.8. This is kilogram times the final velocity square plus the 4.15 joules. And now we rearrange to solve for the final velocity. Adding the terms in the numerator will give us 9.432 joules. P final square will come out to be 11.79 meters square over second square. Taking the square root of the two sides of the equation, V final will yield 3.43 meter per second. And as we expect here, the final velocity is bigger than the initial velocity because the kinetic energy is bigger since the potential energy is less.